So thank you so much for the opportunity to come here and tell you about some of the recent work that I've been lucky enough to participate in. I'm going to be talking about Kilonovae, which I know is a familiar subject for a lot of you, but I'm going to be digging into the nuclear physics of Kilonovae. So hopefully that will be a bit of a, an interesting aspect that might not be familiar. I just want to highlight that I was really lucky for the work in question that I'll be discussing today to collaborate with a really excellent team of nuclear theorists who I've listed here. So this, this work relies heavily on their contributions. I'm really, really grateful to have the chance to have carried it out with this team. Okay, so a definition of terms that possibly no one in this consortium needs, but I just want to make sure we're all on the same page. So Kilonovae are radioactive transients that are powered by the R process decay. So, you have some kind of explosion. Typically, we think of it in terms of the merger of a neutron star with another neutron star or a black hole, and that produces some mildly relativistic neutron-rich material that's gravitationally unbound from the system in one way or another and is outflowing. And this creates the perfect condition for the synthesis of heavy elements through rapid neutron capture or the R process. So basically the R process works under conditions of a very high free neutron flux. So we have some seed nuclei that are flowing out. They're going to be bombarded with a lot of free neutrons and undergo many successive neutron captures. So this is going to produce nuclei that are very neutron rich, heavy, and as a result of the neutron richness, very unstable. So eventually they're going to decay down to stability, mainly through beta decay, but other processes can also be important. So a neutron will be converted into a proton inside the nucleus, and a beta particle, gamma ray, and neutrino will be emitted. So we call this rapid neutron capture as opposed to slow neutron capture, the S process, because the timescales for the neutron capture are much, much less than the timescales for beta decay. So that's, you have this period of successive neutron capture, which produces a different early abundance pattern, different decay pattern, and different, final abundance pattern than what you get if those timescales are more comparable. So, since all of this nucleosynthesis and decay is happening in the context of an expanding outflow, what we end up with is an expanding cloud that's heated by radioactive decays. And of course, that the heating from the decays is going to cause the material to glow. And as everyone knows, that's the signal that we pick up as a kilonova. Okay, so to put it bluntly, one of the goals of multi-messenger astronomy is to really understand well the material that is ejected in the kilonova. So there are a few main properties we're interested in: mass, composition, and velocity. I'm going to be focusing more on mass today, but if we can get a very precise characterization of the material that's ejected in the kilonova, it's going to help us along on a couple of pretty important science goals. So first of all, it will help us understand R process enrichment from mergers, right? If we want to understand the origin of our process material, which because of the exotic neutron-rich conditions it requires has been a very long-standing mystery, we need to be able to measure the contributions from individual channels. So if we can understand our process enrichment from mergers, we can try to understand how much of the total universal R process budget that can account for. The other thing it's useful for is understanding matter at nuclear densities. So we know in neutron star mergers in particular, mass ejection is mediated by neutron star structure. The dominant mass ejection mechanisms and the kind of nucleosynthesis can both carry imprints of neutron star structure. So, and in the case of nucleosynthesis in mergers, it can also be sensitive to the fate of the central remnant, which of course depends on binary parameters, as well as the neutron star equation of state. Okay, so the goal, is, again, is to get as much information as we can from these observations of Kilonovae. And I'm going to focus today on the question of how we can measure the mass of our process material that was ejected by a particular merger. So the first thing that we need to do is unpack the relationship between kilonova mass and luminosity. We can't measure the mass directly, obviously. We have to infer it from the observed light curve. So this cartoon is illustrating a really simple picture of this mass luminosity relationship. In this picture, you just have some energy from radioactivity. It's proportional to the ejected mass, because in the case of a kilonova, all of your mass has undergone an R process, so it's all radiating with some specific heating rate. And then you have some emerging luminosity, which we observe as the light curve. Of course, in the beginning, the system is quite optically thick, and radiation can't really escape, but as it expands, the radiation is able to diffuse out more easily. And so the light curve rises, but at late time, it really just tracks the instantaneous rate at which energy is being input into the system by radioactive processes. This is actually a little bit too simple because we don't have a perfectly efficient conversion from, oh my goodness, I'm sorry. We don't have a perfectly efficient conversion from the radioactive energy, which takes the form of, let's see, so beta particles and energetic photons, as well as in certain cases, alpha particles from alpha decay, or even fission fragments, because in many cases, in the R process, fission is quite important. Only some of that radioactive decay energy actually is converted to the thermal photons that we observe as part of the kilonova. So if we want to make accurate mass measurements, we need to understand both the baseline heating, so that would be this blue curve, as well as the efficiency factor, so what takes us from the blue curve to this purple curve, which is what actually sets the scale of the kilonova light curve. So I just want to give you a heads up. I apologize. I think this next slide got moved out of order somehow. This was, I was going to show you the elements that were produced by the R process. It would have been much better to do that earlier. But now you know. So one of the reasons we're so interested in the R process is that it produces almost half of the elements that are heavier than iron. So if we want to understand where all of the nuclei that we see around us are made, we really need to account for, this channel. And, as I kind of outlined, the physics of it is pretty well understood. We know that we need successive neutron capture, but the problem is that, just nailing down the astrophysical environment can be a little bit tricky. Yeah, I apologize. I have another slide here on the R process that, again, would have been a little bit better to show you earlier before I started getting into Kilonovae and thermalization, but maybe I'll just show you now because I think it is actually useful for Kilonovae. So this is an animation of an R process simulation that was carried out with the Skynet code, which was created by Jonas Lippuner, currently of Los Alamos. And this is just showing what happens in one instance of the R process. There's a lot of information on this plot. In the upper left-hand corner, we're showing the evolution of the gas. So this plot tracks the temperature, the density, and the heating rate as a function of time. In the lower right-hand corner is the abundance pattern, which will change as a function of time. And then, here is the chart of the nuclides, and it's color-coded by abundance. So this is, at the very early stages before the R process has really started. And what we have are some seed nuclei of moderate mass, as well as, it's a little hard to see because it's all packed into this one pixel, but as well as a bunch of free neutrons here. And so, when the R process starts, you can see that neutron capture is driving the system into the heavy and very neutron-rich regions of the chart of the nuclides. Eventually, the free neutron flux runs out, and that's when you see this decay back towards stability. So stable isotopes in the chart of the nuclides are indicated in these black boxes here. And it can take, a long time for the composition to settle down because some of these, okay. I'm sorry, I don't know what happened to my slides. They got quite out of order because now I see that some are repeated, but that's okay. We'll just power through. Okay, anyway, I'm sorry. Some of these nuclei have very long half-lives, but eventually, you're going to settle down and fill out all of these stable isotopes and make those elements that we saw indicated in purple in the periodic table a few slides ago. So, if we rewind the clock a little bit, you can see that the nucleosynthesis happens, in under a second, right? And then we transition to the decay phase, right around a second, and then that lasts several days. So this is the Kilonova phase. This is the phase where the energy from radioactivity is pumping energy into the system, heating it up, and giving you that glow that you observe as part of the Kilonova. Okay, so one major uncertainty in all of these models of the R process and kilonovae is that the composition at early times passes through this heavy neutron-rich region at the chart of the nuclides, and most of the nuclei in this region haven't been experimentally measured, which is a really important source of uncertainty for our process models. Okay, so there are a lot of nuclear physics uncertainties that go into understanding the R process, and I've highlighted just a couple of them here. So a big one, and maybe one of the ones that's talked about most, is nuclear masses. So in cases where we just don't have good measurements for the nuclear masses, we rely on theoretical models to kind of extend the range where we can estimate masses. And then a lot of nuclear physics is set by differences in nuclear masses. So that's a very fundamental input to these kinds of calculations. In addition to masses, reaction rates are also important. And as I mentioned, in a lot of instances of the R process, fission can be quite important. And so, the treatment of fission can have an important impact on the outcomes of these R process simulations. So everything in this column, in column A, is kind of a picture of nuclear theory uncertainty. But there's a whole separate category of unknowns, which is astrophysical parameters. So in addition to nuclear properties, we know that the R process depends on the thermodynamic conditions in the gas and how they evolve in time. So often these conditions are parameterized in terms of 3 variables. So the expansion timescale, how fast the outflow is expanding, the entropy per baryon, and the electron fraction YE, which is a way to quantify the initial neutron richness of the system. And I think it's important to point out that these are slightly different categories of uncertainty. So in the case of the nuclear physics, there is one correct description of nuclear physics, and we don't know it yet, but you can imagine in theory, there could come a time when we have all of the nuclear physics information we need to perfectly model the R process, and that would cut down a lot on our uncertainty. But even if we reach that point, you're still going to have astrophysical diversity because you have different kinds of merging systems, and those are going to produce different astrophysical environments, and that is also going to cause the R process to have slightly different outcomes. So it's important to consider each of these in turn. Okay, and so the goal of the work that I'm going to be discussing today was to understand what all of these uncertainties mean for Kilonovae, and particularly for our efforts to understand Kilonovae and infer their properties from observations. Okay, so in order to explore all of these uncertainties, we first defined a nuclear physics parameter landscape. So we considered 8 different mass models, which are listed here, and those were used to define only unmeasured nuclear masses. So we tried to use experimental data whenever it was available. We also considered 2 different treatments of fission fragment distributions, kind of bracketed expected behavior, either symmetric fission or a double Gaussian distribution. And we also adopted 2 distinct methods for calculating spontaneous fission half-lives. And then, as I mentioned, in addition to all of these nuclear physics properties, it's also important to think about astrophysical conditions. So we, to keep things simple, used electron fraction YE as a proxy for all astrophysical variation, since it's been shown to have a pretty strong effect on our process outcomes, especially in the regime that we're interested in. So we explored all possible combination of these different parameters, which yielded 256 models of the R process. And then we carried out R process simulations for all of them using a nuclear network reaction code called the Portable Routines for Integrated Nucleosynthesis Modeling, or PRISM. Okay, unfortunately, 256 models is a lot to do detailed follow-up on. So instead of trying to do that for the entire parameter space, we instead selected 10 models that were fairly representative. And if you're a fast counter, you're probably seeing that we in fact have 11 models here. So that is because to those 10, we added a single model that actually came from outside the parameter space, but which adopts nuclear physics parameters that are similar to those that are used by some other groups carrying out these kinds of R process calculations. So we just wanted to do that as a kind of a consistency check to facilitate comparison between our work and other people's works. So these are the 11 models that we selected for further study. Right, what we wanted to know is, what do kilonovae associated with these 11 models look like? So I mentioned a few slides ago before we took our R process detour, that in order to model the kilonova associated with any of these nuclear physics parameter sets, one of the most important ingredients we need to know is, both how energy is emitted into the system from radioactivity in each of these models, as well as how effectively it thermalizes. In addition, we're of course interested in the composition. I'm not going to get into it here because it's not a focus of this presentation, but we know that the quantity of lanthanides and actinides, so these particular heavy elements that are burned in the bottom two rows here, right, the quantities of those that are burned by the R process has a very strong effect on the emission. And if you have non-negligible quantities burned, you end up with a kind of a dim red transient that's pretty distinct from the bright blue transient you see if they're absent. So in our case, we were interested in focusing on red kilonova components. So we made sure that all of our models had enough lanthanides and actinides to, to produce red emission. Okay, so sorry, moving back. Right, as I said, these are our models and we wanted to do detailed follow-up on them. So here are kind of the, the important outcomes of our nuclear physics simulations for our 11 models. And then just to demonstrate that they're representative, I've also plotted in grayscale the, similar or the same quantities for the model set as a whole. So on the left-hand side, I'm showing absolute heating rate. So this is the total energy produced from radioactivity before thermalization has been taken into account. The top panel is showing, the total heating rate. The bottom panel is showing that heating rate normalized to a power law, just because a power law is often used as an analytic approximation for the R process. So it's just kind of interesting to see that, while that captures the general behavior, the heating rates often deviate pretty substantially from a power law. And then on the right, there's some information about the composition burned. So here's the total composition with the solar R process residuals indicated in black diamonds. And then, as I mentioned, the quantity of lanthanides and actinides burned is pretty important for the emission. So that is what's shown in this bar graph here for every model. Okay, so yeah, I think the two important, the major important points to take from this is that just from nuclear physics variation alone, we get obviously a pretty big spread in composition. We also get a pretty big spread in absolute heating on kilonova timescales. So that's what's indicated in this red bar here. We see differences of, almost an order of magnitude between the top heating and the bottom heating models. Okay, I mentioned earlier that what's important when we're thinking about kilonova luminosity is not just the absolute heating as shown in this plot, but the effective heating. So heating, that accounts for the fact that not all of this energy is thermalized. In the interest of time, I'm going to skip over the details of the thermalization calculation, but I'm definitely happy to talk about it in a lot of detail if anyone is curious. Instead, I'm just going to show you the results. So these plots show the ratio of thermalized energy to emitted energy for each model, and I've broken it down by decay product. So over the course of an R process, a lot of nuclei undergo beta decay, which is going to produce gamma rays, beta particles, as well as neutrinos, which don't thermalize at all. But we can get alpha decay and fission. And it turns out, as you can see from looking at this plot, in the cases where alpha decay and fission are important, they actually have a very significant role in boosting the heating. So, right, so sets of nuclear physics parameters that support non-negligible amounts of alpha decay and heating tends to have a higher thermalization efficiency than the nuclear physics parameter sets that are restricted to beta decay. I also want to point out that thermalization efficiency depends, in addition to nuclear physics, it depends on ejecta parameters. So to just isolate the role of nuclear physics, we've carried out all of our calculations for a single set of ejecta parameters. Okay, so let's see, yeah. And I think, again, the main thing to notice here is just like we had very diverse heating rates, we now have very diverse thermalization efficiencies. So you're taking variable thermalization rates, applying them to variable heating rates, and not surprisingly, that's going to give you a pretty large range in effective heating. And again, effective heating is the energy source for the kilonova luminosity. So this is what determines, the luminosity budget of the transient that we would observe for this kilonova. All right, so this probably, it really doesn't look too different from the absolute heating. The story is basically the same. There's a large range in terms of both the magnitude of the heating and its slope. You can get some interesting behavior here where like a fission becomes important at a certain time. You'll see a flattening of the slope. Yeah, you don't necessarily have these nice clean power laws. You have something that looks a little bit messier. However, we cannot observe effective heating rates. So what we're really interested in are light curves. So these are the light curves, the bolometric light curves that are associated with each of these models. And not surprisingly, they're also pretty variable since they're powered by extremely variable heating rates. But beyond the variability of the light curves, there are three additional important points that I want to emphasize. So the first has to do with these high opacity lanthanides and actinides that I mentioned. So I've reproduced here the bar plot that we saw earlier showing lanthanide and actinide mass fraction for each of our models. And if we're looking at this closely, and if you're familiar with Kilonova modeling literature, it's probably already occurred to you that the lanthanide and actinide content in a lot of our models is much higher than what is typical in the literature. Okay, and you might be concerned about this because we know from earlier work that lanthanides and actinides are very high opacity atomic species, as I mentioned. So, that produces this clear trend between kilonova behavior and lanthanide and actinide content, as you can see from these one-dimensional radiation transport simulations for 4 models that differ only in their composition, right? So as we start with a very low quantity of lanthanides and actinides, and as we crank that up higher and higher, the light curves become, elongated, and they have dimmer later peaks. I'm not showing spectra for these models, but were I just show spectra, you would see that the emission also became redder, but we'll talk about that a little later on. Anyway, in our models, we actually see that the trend between light curve shape, or the relationship between light curve shape and lanthanide content, is not fully upheld. So I guess just to point out an example where the trend is broken, you can see model 8 and model 5 both have fairly high lanthanide and actinide mass fractions, with model 8 being slightly higher. And yet this model produces a light curve that is narrower, which is a little bit, counter to the trend that you see in the left-hand panels. But the reason the trend is broken is just that all of the models on the left-hand plot were calculated for a single R process heating rate, where for the models on the right-hand panel, heating rate and composition were varied in a self-consistent way. And it turns out that heating rate affects the light curve shape. So you can show this mathematically if you carry out some of these like simple Arnett-like models of radioactive transients, but you can also just understand it intuitively. In that a shallower heating rate is going to be able to compensate more effectively for energy that the system is losing, whether to diffusion of radiation or adiabatic expansion, and that's going to stretch out the light curve just the same as an increased opacity could. Okay, and to make this point a little bit clearer, I'm going to show you 3 sets of calculations for our models. So I've changed the color scheme here. So in this case, the color indicates the lanthanide mass fraction that was predicted for each of our simulations. In the plot on the right, the composition, we've kept the composition predicted by the R process calculations, but standardized the heating rate. And in this case, you can see there is this really nice, clear relationship between lanthanide mass fraction indicated by color and the shape of the light curve. The middle plot is just what you've seen before, the light curves where both the lanthanide mass fraction and the effective heating rate are varied in a self-consistent way. And in the plot on the right, all of the models have a standard lanthanide mass fraction, but the heating is preserved. So I think these plots are nice because they show that heating has at least as strong of an impact on light curve shape as lanthanide mass fraction does. Okay, and if you look at the middle panel, there are a few other odd things about some of the light curves that I want to talk about next. So that is some of these surprising features at early times. In particular, some of these light curves even have like a double peak or a really significant excess at early times. So in the last couple of minutes, one thing I want to talk about is the role of ionization state. Okay, so to really understand the importance of ionization state, we have to talk a bit about opacity. So opacity for Kilonovae, the most important source of opacity is just bound-bound opacity, which means that an atom is absorbing a photon. And bound-bound opacity is temperature dependent. And this is this really nice plot from Masayomi Tanaka's recent paper shows that temperature dependence. So this illustrates how atomic energy levels are distributed as a function of energy above ground state for +1 ions. But the picture is the same for different ionization states. So there's a scarcity at low energies, but you start to get a more and more density of these, a greater and greater density of these energy levels as you move a little bit farther from the ground state. So the more energy levels are populated, the more bound-bound transitions are accessible. So just the more different, let's see, you have a greater diversity of atoms in a greater diversity of states, able to absorb a greater diversity of photons as they travel through, and that has the effect of increasing the opacity. If you crank your temperature up too high, you end up ionizing atoms, and then you start all over in the ground state. So you kind of have this periodic effect when you talk about the relationship between ionization state and opacity. So that's what's shown in this slightly less beautiful plot, but hopefully it's still informative. So this is showing the Roslin mean opacity in solid lines and the average lanthanide ionization state, chi, as dashed lines as a function of temperature. And just as you would expect based on the discussion in the last slide, you see that that opacity really drops off as the lanthanides and actinides are becoming doubly ionized. So that's because, again, all of the ions in that case are confined to a handful of low-lying states. And that means there are fewer distinct opportunities for photon absorption, and that produces a local opacity minimum. Okay, I'm sorry, I see that I have not timed this well. So in the interest of time, I'm going to try to accelerate the discussion to make sure we cover everything. But I want to, I want to make sure I discuss the effect of ionization state on the bolometric light curve. So let me see if I can do that very efficiently. So in some early models of Kilonovae, the low opacity region didn't have much of an effect because it was kind of buried deep in the ejecta. And so, the Kilonova evolution was set by the higher opacities of the singly ionized layers that were found in the outer regions of the ejecta. This plot is showing, let's see, it is showing the contour part of the plot is showing the ionization state as a function of interior mass coordinate as a function of time for an ejecta model. And then this black curve is showing the surface where the Rossler mean opacity is equal to 1. So this line just kind of passes through the surface that is responsible for setting the effective opacity of the kilonova. So this represents a typical kilonova model where you have this highly ionized low opacity region, but it's deep in the interior and the effective opacity is set by exterior regions. What has changed in some of our newer models is they have much higher rates of heating. And so that pushes the highly ionized region out towards the edge of the ejecta, and where it is able to have an effect on the effective opacity of the kilonova and therefore on the light curve evolution. So this is showing an extreme case of that, one of our cases with very high heating. And in this case, you actually end up getting a double peaked light curve. So early on in the kilonova evolution, the effective opacity is set by this low, doubly ionized region. As the system expands and cools, ionization fronts sweep inward. So eventually, the outer regions become singly ionized again, and that kind of resets the kilonova ejecta to a higher opacity state, and that allows the light curves to rise again. Okay, and we found that, depending on the level of heating, and you could get kind of a variety of signals from this clear double peaked light curve to an extended shoulder on the light curve tail to an early excess to nothing at all. So this is just one way of showing that from heating alone, without considering composition or any other effects, you can get a fair amount of kilonova diversity. The final thing, and I apologize, I'll try to make this really quick. The final thing I want to talk about is color, because as I mentioned, there's this expectation that as you increase lanthanide content, you get redder and redder kilonovae. So given the high lanthanide content in some of our models, it would be reasonable to wonder if we get kilonovae that just look bizarre compared to other compared to other models or compared to observations. So, and I'm sorry, this slide came from a talk I gave to theoretical physicists, so please forgive the bluer versus redder guide for magnitudes. Okay, so two things to mention. The first is just that at very early times, some of the high lanthanide models are actually, very blue. So here I'm showing R minus I and I minus H colors at times less than 5 days. And the models that are consistently blue have some of the highest and some of the lowest lanthanide content. And that's because early color is related, at least in the high lanthanide, it is because some of these models that have very high lanthanide mass fractions also have high heating. And so their early colors actually are reflective of this doubly ionized region, which has this lower opacity, so you see deeper into the ejecta where it's bluer. So you can get these counterintuitive trends where you have lanthanide mass fraction, but it's not, you don't necessarily get this monotonic relationship between color and mass fraction, especially at early times. At later times, the situation changes. These high lanthanide cases don't maintain their blue color forever. But what we see instead is that there's actually a fairly kind of standard set of colors. Okay, so this is showing, again, select colors as a function of time normalized to bolometric peak time. And we do that just to more easily compare light curves that have a very broad range of timescales. Okay, and again, you see the lowest opacity models are sort of doing their own thing, which makes sense. But the other models all show fairly similar color evolution, even though they span a very large range in mass fraction. And you can also see this by looking at spectra. So these are the spectra of each model taken at bolometric peak. Okay, and again, if your lanthanide and actinide mass fraction is pretty low, you do get a characteristic blue color. But after that, once you reach a threshold that seems to be about 0.1 for lanthanides and actinides further increases don't really change your spectrum that much. So, all of these cover a pretty broad range in lanthanide and actinide mass fraction, but they have pretty similar spectra. And so what that tells us is that, you can't necessarily rule out some of these high or some of these very lanthanide rich models just from color evolution alone. Okay, sorry. So I will just end here. Back to another cartoon that hopefully summarizes the major points. All of these nuclear physics uncertainties just mean that there's another degeneracy that we should be thinking of when modeling kilonovae and when interpreting their emission. So, if these red stars are data and we assume that we absolutely know the R-process heating rate and it's represented by this blue curve, then it's fairly straightforward to estimate the mass from observed luminosity. Once you know the mass, you can fix the velocity and the opacity to be consistent with observations. And you would do that just by, I know these are obviously gross simplifications of the kind of analysis that goes into the interpretation of data. But I think, these are just cartoons to sort of document what kind of reasoning goes into the model building, right? If you need a brighter kilonova, you can up the mass. If you need a wider kilonova, you have to increase the optical depth. So you're going to raise the mass, raise the opacity, or maybe lower the velocity. And you just kind of have a limited set of knobs to turn, and you can make these measurements fairly confidently. Although, of course, there are other factors at play, like orientation or multiple components that I haven't touched on here today. But, if your effective heating rate could span, a large range, or if it's uncertain in any way, then that means there's a lot less clarity in this kind of analysis because there are these extra knobs that we can turn to try to match an observation. Okay, so yeah, I apologize, that ran a little longer than I thought. Definitely happy to take questions if anyone wants to stick around. Again, thank you for sticking with me and thank you for the invitation.